Hi everyone, and welcome to the first of 4 videos going through some past exam questions on bonding and structure. So this first question is asking us about the periodic table. Early attempts at developing a periodic table had the elements in order of increasing atomic mass. State which 2 elements from the first 20, which has got to be from the first 20, are not arranged in order of increasing atomic mass. Okay, so we just need to go across the periodic table here and find them in terms of mass. So hydrogen's atomic mass is 1, 4. So we're just going to check every number and see if it increases every time. Fit this in. Yeah, that goes up. 10, 12, 14, 16, 19, 20. Then we've got sodium is 23, 24, 27, 28, 31, 32, 35, 40. And then potassium is 39. So this is the one. Argon is 39.9 and potassium is 39.1. Okay, so it's argon and potassium. Okay, why does the periodic table not arrange these elements in order of increasing atomic mass? Well, this is because the modern periodic table has all the elements in order of atomic number, doesn't it, instead? Arranges all elements in order of increasing atomic number. Okay, right, then it says the group 2 element barium was isolated by Sir Humphrey Davy. Okay, has a giant metallic structure. Describe with the aid of a labelled diagram the structure and bonding in barium and explain why it has a high melting point. Okay, so a giant metallic structure, that is going to be a lattice of metal ions surrounded by delocalized electrons. So we're going to have some, barium is in group 2, so we're going to have some Ba2 plus ions. Okay, we're going to try and show those in some sort of organized layers. Something like this. Right, so here's my barium ions. And around this, there's going to be electrons all over the place. And so let's label this up. So let's say, so we can say this is positively charged ions. And we've got here delocalized electrons. So we can say barium has a giant metallic lattice, or let's say barium's structure is a giant metallic lattice. And then to explain why it's got a high melting point. So if there's a high melting point, it's because the forces that are holding it together are strong and take a lot of energy to break. So what's holding this together is the attraction between the barium ions and the delocalized electrons. So we can say there is a strong electrostatic attraction between the positive ions and delocalized electrons. And then we say that requires a lot of energy to overcome. It's always worth putting that in when you're talking about bonding, especially when you're linking it back to melting point. It requires a lot of energy to overcome. Okay, so that's what our metallic structure should look like. Right, moving on here. So we've got a sort of linked question here where we've got some various different elements in period 3. It's given us the melting point and the radius. So explain the difference in melting point for sodium and magnesium. So this again is going to be a metallic structure. Okay, so we can put this in. So sodium and magnesium both have a giant metallic lattice structure. But we can see magnesium's melting point is higher. So we said that, we've just written this, haven't we, in the previous question, that the melting point depends on the strength of the attraction between the positive ions and the delocalized electrons. So if magnesium's got a higher melting point, it must be because there's a stronger attraction between the ions and the delocalized electrons. And the reason for that is because as we go across the period, sodium's in group 1 and magnesium's in group 2. So magnesium is going to have a 2+ ion, so it's got a higher charge than the sodium single plus, and it's also going to have 2 delocalized electrons per atom, whereas sodium's only going to have 1. So therefore there's going to be a stronger attraction because you've got more electrons to be attracted, and you've got a more highly charged ion for them to be attracted to. So we can say the Mg2+ ion has a higher charge than the Na+ ion, and magnesium has more delocalized electrons than sodium. So in magnesium, there is a stronger attraction, let's say a stronger electrostatic attraction between, I'm going to run out of space here, between the positive ions and delocalized electrons. And then we're going to say the same thing we did on the previous question, which requires more energy to overcome. Okay, I always like to add that in. Sometimes you get yourself an extra mark just by putting that. Okay, so that's our sodium and our magnesium. Right, then it's asking us to compare sulfur and chlorine. Sulfur exists as S8 molecules and chlorine as Cl2. Use this information to explain the difference in their melting points. Okay, so the melting point, we can see sulfur is 113, chlorine is -101. So sulfur has a much higher melting point. So if we're talking about molecules, then we need to be talking about intermolecular forces. So if sulfur's got a higher melting point, it must be because the intermolecular forces are stronger. Because these are just elements, then the only intermolecular force that we can have is London forces, because there's going to be no chance of making a dipole, because it's just going to be all the same elements. There's no difference in electronegativity. So it must be that sulfur's London forces are stronger than the London forces that are in chlorine. Okay, and that makes sense, because if you've got S8 molecules, remember the strength of London forces depends on the number of electrons. So if I've got 8 atoms, I'm going to have a lot more electrons than if I've just got 2 chlorine atoms. Okay. So we can say S8 molecules contain more electrons than Cl2 molecules. So sulfur has stronger London forces. And then we're going to put the same point in again, so we can say these intermolecular forces. It's worth just making it clear that we know that London forces are an intermolecular force. These intermolecular forces require more energy to overcome. Okay, final question here. It's saying solids exist as lattice structures. Giant metallic lattices conduct electricity. Giant ionic lattices do not. If a giant ionic lattice is melted, the molten ionic compound will conduct electricity. Okay, and we need to explain this. Okay, so giant metallic lattices conduct electricity because they contain delocalized electrons. It's worth just making it clear that we know what that means. They contain delocalized electrons which can move through the structure. Solid. So then we're saying the solid giant lattice doesn't conduct, but when it's molten it does conduct. Okay, so solid giant ionic lattices do not conduct electricity because the ions are unable to move. Okay. When molten, the ions are able to move. So the ionic compound does conduct electricity. So we need to be careful with this question that we don't start talking about delocalized electrons with the ionic lattice. Okay, that's a very common mistake that I see. Ionic lattices do not have delocalized electrons under any circumstances. It's the ions themselves that we're looking for. Okay. Basically, for something to conduct electricity, you need to have a charged particle that can move. So in a giant metallic lattice, you've got the electrons that can move. In a giant ionic lattice, the charged particles that you've got are the ions themselves. And when it's a solid, those ions can't move. And when it's melted or dissolved in water to make it aqueous, then those ions can move, so it can conduct.